opportunity to present my work. I'm from University of São Paulo, campus São Carlos. Differently from Floripa or Natal, there is nothing to show, so I will not do that. As John mentioned, the topic of my talk is energy exchange and entropic analysis in a dipole single-photon system. And the idea here is we wish actually, and these are joint work with Daniel Valente, Robson Ferreira, and Thiago Verlange. And our idea was through the analysis of a very simple system that's experimentally feasible with the state of the art in the lab now, trying to using the minimal framework that we have available, that we think we do not dispute, and try to see if we can, how far we can go in the description of the thermodynamics, the energetics, and entropic analysis of my system. So essentially, we decide to take this route because if you are in the field, I don't know about you, sometimes I have this impression when I look the archive of the day, we see several routes of people thinking differently, and this is natural because the field is quite young. But sometimes you have the feeling that there is some confusion and we need to clarify things. So hopefully, at least our route, that we will be based only on quantum mechanics of our universe, and from there try to extract the quantities that we are used to observe in thermodynamics. So, of course, the field has several open questions. Yeah, the first one, I think, is does it make sense? If you are orthodox in the field of thermodynamics, probably not, but we are here and we are trying to make sense of things. The other good question is, should we expect some advantage? It's not clear. And 2 points here that I will address in my talk. I mean, we will be very interested in this regime is when we have the very strong coupling between the environment, the bath, and the part of your universe that you are interested in quantifying, in observing. And another thing that we will be very interested in is the opportunity of looking at different initial conditions that are not thermal states. Okay, so we want to explore the possibility of having out of equilibrium states and see if we can make sense at all in this picture. So, as I mentioned, our model will be very minimal. So we will assume that our universe is quantum, and no classical terms are allowed to put in the Hamiltonian. Okay, so I will not have an external magnetic field applied to the system and change that. I want everything emerges from the description of the universe. And I will allow to have my system in a non-equilibrium initial state. Okay, so for that, I need my commandments. And the idea is the universe will be quantum. Okay, and it will evolve following the Schrödinger equation. Then, if I'm interested only in looking at a part of my universe, everything that I will observe from it is extracted from the reduced density matrix, okay, from that universe. Another commandment is that I do expect it to have the classical dynamics emerging of this description, okay? And that's important because with that I under the conditions that I would expect classical dynamics or classical results, classical thermodynamics, I try to connect with the results that we get. And finally, we assume that unitary evolution shall preserve entropy. So those are our commandments. As I mentioned to you, the model is quite simple, but we think it's experimentally feasible. So in the lab, one of the implementations is if you put embedded a quantum dot in a nanowire, and the nanowire can conduct light and interact with the quantum dot, for example. So this is my theoretical picture. You know, it's much worse than the experiment, but this gives an idea. I will have the system interact with the electromagnetic mode. Okay, I will pass a pulse through my waveguide, my nanowire, and I will see the dynamics. What happens? What emerges from this description? Only to give a perspective, from the classical point of view, the work done by this pulse passing through the dipole is computed, the rate in time is computed as this expression. It's quite simple. D here is the dipole. If I have a classical electric field and a quantum dipole, I change a little bit, and I have an expected value for the quantum dipole. But everything is standard and well characterized in the literature in quantum optics. So now I will present the Hamiltonian. So my universe is composed by the system, the dipole, the electromagnetic field, and the term of the interaction between them. And no assumption will be done about the strength of my dipole and the electromagnetic field. So my dipole is a two-level system, electromagnetic field, a collection of modes, bosonic modes, and I have a dipole interaction, standard one. Okay, and this kind of Hamiltonian has the feature of conserving number of excitations, and that's what allows us to provide analytical expression. Okay, because I want to avoid the main criticisms about any kind of implementation regarding quantum thermodynamics. That is, we want, when you are in the weak coupling limit, it's quite straightforward. We have results connecting the standard thermodynamics with quantum thermodynamics. But going beyond this regime, it's not clear that things can work out. Okay? So I will not allow, from this point on, to have approximation. That means that I will be capable of providing an analytical solution for the evolution of my universe. And since I have everything about the universe, I can extract the information of the part. Okay. So my limitation is I will work with the scenario that I only have 0 or 1 excitation in my universe. Okay? And due to that conserved quantity, the excitation is a conserved quantity here, I know that if I start in this subspace, 0, 1 excitation, I will stay in this 0, 1 excitation. So under this assumption, I can write the state of my universe as general as I can assume. And using the Schrödinger equation, I can compute all the amplitudes that I have for the general solution. Okay, so here, for example, is the component of the vacuum for the electromagnetic field, and the ground for the ground state for my dipole. Here I have my dipole excited, but nothing in the electromagnetic field. And here I have my two-level system in the ground state and 1 excitation in the electromagnetic field. Okay, so doing some calculation, I can write the formal solution for the evolution of the amplitudes of my state, my general state, in terms of the initial conditions that I have assumed. Here, I haven't assumed any specific initial conditions, besides that I'm still in the 0-1 excitation subspace. Okay? So, only to remind you what we have, if under this perspective, under this condition, if I look for the expected value of the dipole, I see the expected value of the dipole is 0, and also expected value for the electric field under this condition is 0. Okay, and then if you look for the classical description or the semi-classical description, both would give you 0 work under the system, under the two-level system. Okay, but when I look for the reduced part, for the part that I'm interested in, the two-level system, namely the two-level system, what I see is I can write the density matrix, and I see these terms. So, as you can see, I have coherence. E and G are the eigenenergy bases, okay? And I see coherence under these assumptions. Also for the BEF, for the environment, here I'm calling the BEF the electromagnetic modes, even though the initial state for the electromagnetic field is not a thermal state. That's really important. But I have a continuum of states, I have a continuum of modes available for my electromagnetic field. So what this slide shows us is, indeed, once I know the initial conditions, the initial condition for my two-level system and the electromagnetic field, I can provide the description for the parts, both of them. And then, without any other assumption, I can derive in having a master equation for the part, without any assumption. Okay? So I do the derivation in time, and what I see is this kind of a master equation. The same for the electromagnetic field. Okay? And the most important thing is, okay, with this result, here, I can write the master equation in this form, with a shape of a Lindbladian equation, master equation. But here you see the rate changes in time. Okay, so this master equation is not assumed. It's derived from the description of the universe. That's really important. And what we see here is the dipole. Initially, we had assumed that the gap is constant. But due to the interaction with the poles that we are passing through the waveguide, it gains a time dependence that physically is associated with we were stretching or compressing the dipole. Okay, so we gain some dynamics for the gap in this reduced description, and that allows us to have work done under the system. Okay, and we can determine the rates. So once we have the full description of our universe, we can derive everything. And that's the point, because then I don't have to make any assumption. And here is the same, I mean, just to show you that we can get similar expressions for the BEF, the electromagnetic field. And one thing that emerges here is, if I take the effective Hamiltonian that appears here in the equation of motion for the system and also for the BEF, what we see is the expected value contains the half of the interaction between the electromagnetic field and the dipole. It's natural. We didn't have to assume this, and when you do the calculation, you see that under this framework, it is split equally between the two systems. Of course, that means that the expected value of the universe is the sum of those. So everything is consistent under this perspective of expected values of energy. And then we will do the entropic analysis, okay? So, I don't know, probably I was too fast, but for the density matrix of the part of the two-level system, we had all the possibilities, a two by two matrix, and we had of diagonal elements in this basis, and this the eigenenergy basis. And so we had coherence there. But if we do psi naught equals 0, so if I have an initial condition where psi naught is 0, what I gain is this density matrix that will evolves in time. And the point here is, this is a two-level system in the eigenenergy basis, and this is diagonal, okay? For the bath, for the environment, it's not the same. It's not diagonal in the eigenenergy basis, okay? But I can look at this guy here and go further, because under this perspective, this state, this state is an honest thermoequilibrium state, meaning that I can associate a temperature, okay, due to the ratio between the populations here. There is nothing different from this state from a thermal state that was connected with a thermal bath, okay, with inverse temperature beta. Okay, so in this point, since I have an equilibrium thermal state, I'm in a safe position to recover the standard thermodynamics that we learn in the course and see if we can connect the change of entropy with heat generated here. So again, since I'm working with thermal states, I have no problem using von Neumann entropy, for example. It's a good measure for entropy in this situation. And then, if I look the variations, I see after some simple calculation that I can relate the change of entropy with this quantity divided by T, and T here is the effective temperature that I can associate with this state. Of course, if I go to thermodynamics, under this situation, I would expect to have this relation because I'm in a succession of thermal states, okay? My protocol takes my system, my two-level system from a thermal state to another, change temperature, and then with this kind of framework, I could compute the heat associated with the process, you know? And then what? The problem is, and I will not hide from you, this is the amount of heat that we computed using entropic relations. That's very important. I'm not defining heat, assuming this or that. I'm looking at the expressions. I have the connection with the standard thermodynamics, and I was supposed to call this heat. But the point is, this expression here can be written in several ways. Okay? So each way here, each one gives me the same value for this heat that I have. Okay? So you said, you can think, okay, there is no conclusion about this kind of experiment could give us some light in, about the definition of heat and work, that we know it's something that is under dispute right now. The same for work. For work is quite simple, since I have just to apply, require the first law of thermodynamics. Okay, no problem. So for example, if I look at this definition, that gives me correctly the amount of heat associated with the process, I would have the work written in this way. And this, if you look at for the in the literature, you will see that this is a kind of extension of Alick's work of 1979. The only difference here is the Hamiltonian, the effective Hamiltonian for the part, for the two-level system, or for the environment, is not the bare Hamiltonian that you had before. Okay? It's an effective Hamiltonian that emerges from the interaction between the system and between the parts of my universe. So that's why we call some extension. Okay, but fortunately, at least at this level here, we can go beyond. So if I assume that C0 is not 0, then if I go all the procedures using all those quantities that provide me the same result that is correct for the standard thermodynamic point of view, what I see is one of them, this one, is different from the other three. So I showed you 4 types of writing the work that were consistent with the picture that we had before. And now, due to the fact that psi naught is not 0, I would have one of them different from the others. So the point is, if I go to the experiment and I measure the amount of work and the heat that is consistent with these 3 expressions, that they are the same, I will not conclude which one would be the best to define heat and work. But for example, if I'm lucky, I mean, if nature says to us that indeed is this quantity that is what we observe in the experiment, we had settled the problem of the definition of heat and work. Okay. So I'm running out of time, sorry. The point is, here, with this minimal model, we could go thus far, and we can go further in the sense that we can provide means or to tell the experimentalists how to measure the quantities and check the definitions and the results that we got. Okay, so I will skip this one, but indeed we can provide a scheme where you find means to realize which one, at least from those 4 forms, would be the correct form for heat and work. So the take-home conclusion here, or the message is, perhaps we are already in position of testing and ruling out definitions of heat and work that we have in the literature, in the market, you know, and by means of staying with the minimal framework that we can have. I mean, if we go from quantum mechanics and derive all the evolution, everything consistent with our model, we can perhaps realize and decide which definition would be the consistent one, even for out of equilibrium situation and the strong coupling limit. So with that, I thank you very much.